All right, we're going to talk about net ionic equations, which applies to double replacement precipitate reactions. Net ionic equations show what really happens in the water when we make a precipitate. So, we should remember that when an ionic compound actually dissolves in water, it breaks apart into its ions. That's why it can conduct electricity, because the ions are now all separated and can move around. So remember, like table salt, when we drew table salt, it looked like this, plus minus, plus minus, plus minus in a lattice. But when we pop that into water and the table salt dissolved, the ions all separated from each other. Okay, so that's when you have an aqueous ionic compound. Is actually what it looks like. But on our solubility chart, we know that some ionic compounds do not dissolve in water. Those are the ones that we see as a solid. So if we put those into the water, they end up still sticking together. And that's why they do not dissolve, because they stick together as a solid. So you can see those examples here. So when you have sodium hydroxide that dissolves in water, the sodium and then the hydroxide ions are apart from each other. Now notice I put the charge in because they are ions. Copper nitrate also dissolves in water. When it does, the copper ions separate from the nitrate ions. Now notice that I do not have this in parentheses as such that you see in the formula, because when two nitrates split apart from each other in the water, it's a nitrate and then a separate nitrate. They're not combined. Now, how did I know the charge on copper was +2? Well, the charge on nitrate's -1, and if you have two of them, then the charge of copper has to be +2. Now, copper hydroxide, on the other hand, does not dissolve in water. So you will not see me break it into its ions, because that's why it's a solid. It sticks together. So let's just get practice on figuring out when an ionic compound dissolves in water, how many of each ion is present, because that's going to be important in the work that we do. So for example, if one set of this compound breaks down into its ions, we're going to have 3 separate H pluses, H plus, H plus, H plus. To show that they're all separate from each other, that 3 comes out in front. It is not a little subscript anymore. And then the phosphate comes apart. We just have one set of that. Now, if we have 3 sets of these compounds breaking apart, that means we have 3 sets of H plus, H plus, H plus. So if you have 3 sets of 3, that's 9 hydrogen ions. But that 3 also applies to the phosphate. So we're now going to have 3 phosphate ions floating around. If we have 6 sodium hydroxides, that means we're going to have 6 sodium ions and 6 hydroxide ions floating around. Maybe try out the rest on your own. We'll see. You might have to do a little detective work to figure out the charge on the transition metal. So, for example here, if I have 2 nitrates and they're both -1, the charge on copper has to be +2. When I did that, I ignored the 2 out in front, just so you know. So I have 2 nitrates, they're both -1. The charge on copper has to be +2. Now, but when I split them up into their ions, I'm going to have 2 copper ions floating around. So 2 sets of copper 2+. And I have 4 sets of the nitrate ion floating around. Here, I'm going to have to figure out the charge of iron because it's a transition metal. Sulfate is -2, and I have 3 of them. Iron, I have 2 of them. So what must be the charge of each iron if it's going to balance out this -6? They must both be +3. But I have 2 sets of 2 irons. So when that breaks apart, I get 4 iron ions with a charge of +3. And think about how many sulfates that would be. I'd have 6 sulfates with a charge of -2, because 2 times 3 is 6. 2 sets of 3 is 6. All right, the charge of lead here also has to be +2, similar to how the copper was +2 over here. But I have 3 sets that are going to break apart. So 3 lead ions and 6 nitrate ions. Okay, so that's just a little part of what we're going to be doing. So let's look at an overall, what we call net ionic equation. So we often write double replacement reactions to represent the formation of the solid precipitate in what we call full ionic and net ionic equations. So for example, you'll see me say molecular equation. That is the reaction that we have been writing down in our notes so far. It just shows the full-blown double replacement reaction where we have the formation of the solid precipitate. Now, anything that's aqueous and ionic is not really stuck together like you see here. Because we know that when we have aqueous ionic compounds, the ions are actually split up from each other like this and like this. So what we call the full ionic equation, if you notice, anything that's an aqueous ionic compound, like salt, silver nitrate, sodium nitrate, we break that up into its ions. So sodium chloride breaks up into the sodium ion plus the chloride ion separately. Silver nitrate is going to break up into silver and nitrate ions separately. Sodium nitrate breaks up into sodium and nitrate ions separately. But if you have the solid precipitate, it does not break up into its ions. So we keep that written exactly as is. So the big idea is that when we go from the molecular equation to the full ionic, all we are doing, it seems very complicated, but literally all we are doing is breaking up anything that is aqueous into its ions. Now the details are figuring out the charge of those ions and how many you're producing. So that's kind of like what we were practicing up here. All right, now that's what we call full ionic. To go from net ionic, notice that there are some ions that are on the left side of the reaction that are the exact same as what you see on the right. Do you notice any? Sodium is one. If you notice, we have a sodium plus ion on the left and a sodium plus ion on the right. Those are going to what we call cancel. If you have one on the left and you have one on the right, that means the sodium ion did not change whatsoever. We have another one. Can you see it? It's nitrate. One on the left, one on the right. That means the nitrate did not change whatsoever either. So can you imagine, like in sports, what those people are called when they just watch the sport? They don't actually participate. We call those spectators. And in these reactions, these ions are just looking at the reaction. They're not really reacting themselves. So we call these spectator ions. They get removed, and the remaining is left for the net ionic equation. So we remove the spectator ions. So if you notice, after we remove it, we have the chloride ion plus the silver ion make the solid precipitate. You'll find that the net ionic equation shows the formation of the solid precipitate. Precipitate, PPT. That's a shorthand. And this is the picture of what's happening here. So this is our silver nitrate solution. Remember, it's aqueous, the ions are broken up. That's what it looks like. And then we have our salt solution, the NaCl. It starts off aqueous, everything broken up. But when we mix them, the silver ions from this solution find the chloride ions from this one, and they get together and form the solid precipitate. Now the sodium ions are still sodium ions. Those are the spectators. The nitrate ions are still nitrate ions. Those are the spectators. Those get removed. Okay, so let's get some practice from start to finish. Now, just to save time, you can pause this and try this out. You're just predicting the products of this reaction. But to save us time, I don't want to make this video super long. I'm just going to give you the products. Now, I know that copper has to be +2 here because the two nitrates are -1, and that makes the copper +2. Looking at my solubility chart, copper carbonate is my solid precipitate. Sodium nitrate is my aqueous solution. Now to balance it, we're going to need a 2 out in front of sodium nitrate. Okay, So that's our molecular equation. We already know how to do that. We're now going to do our full ionic equation. To do that, this is the only thing we have to do. Break up anything that's aqueous into its ions. That's it. Now the details are figuring out what charge the ions are and how many you have. So sodium, I have 2 of the ions. If you look at the periodic table, they're both +1, but they're going to be separate, not together. So I'm not going to keep the 2 down there because that implies that they're stuck together. To show that I have 2 separate Na pluses, like Na plus and then another Na plus. The 2 comes out in front. And it's aqueous. Carbonate is separate from the sodium now. I only have 1 of those. It's -2 if you guys check your polyatomic ion chart. Copper is aqueous. Copper nitrate is aqueous, so I'm going to break it up. Copper is going to be +2, and I only have 1 of those ions. How many nitrates do I have that are going to be split apart? 2 of them. They're going to be separate from each other, though. So that 2 is not going to be written as a little 2. That 2 is going to come out in front to show that I have 2 separate nitrate ions. Okay, should I break this one up? Heck yes, I should, because it's aqueous. So that's going to break up into sodium and nitrate ions, and let's think about how many we have. That 2 out in front applies to both the sodium and the nitrate. Both are aqueous. Should I split up the copper carbonate? Absolutely not, because it's a solid. Solids stick together. That's why they're solids. So I'm just going to rewrite it exactly as written, including the 1 that's out in front. But if you don't put anything, it's an implied 1. Okay, so one thing that you always want to double check is that you did put the charge of everything that is broken up. That's something that is often overlooked. Now we're ready to go into our net ionic equation. That is when we look for spectator ions. So ions that are on the left that are the exact same as what you see on the right. So that would be my 2 sodium ions. Carbonate, that changed. Copper, that changed. But the nitrates did not. Those are spectator ions. So we're going to cancel those out. And what you should always have left over is the formation of the solid precipitate. It should also be balanced. If you have a copper on the left, you should have 1 on the right. If you have a carbonate on the left, you should have 1 on the right. Our spectator ions were also balanced. Notice we had 2 sodiums on both sides, 2 nitrates on both sides. So as long as everything is correct still, it should be a balanced reaction. That's a way to check yourself. Okay, if I were to draw this at the particle level, I'm basically kind of drawing what I drew for the full ionic equation, just more so in drawing form rather than equation form. So for my reactant, sodium carbonate, it was aqueous. So that meant I had sodium ions and carbonate ions floating around. For the copper nitrate aqueous solution, I had copper ions and 2 nitrate ions floating around. Now my products, when these were combined, remember the copper and the carbonate got together and they formed that solid product that's stuck together. They're not separate ions. They're stuck together as a solid. But the other ions, the sodium and the nitrates, those are still floating around, separate from each other because they're aqueous. All right, that's what we mean by the picture. It's just taking the full ionic equation and just drawing a picture of it. All right, to save you guys time, I'm going to give you the products. And we can balance it. All right, so remember to go from a molecular equation to full ionic. Break up anything that is aqueous into its ions. I can give you a head start. Maybe pause the video, try it. I'm going to go ahead and do it. So aqueous, I'm going to break it up. That's going to break up into 2 lithium ions, which are both +1, and 2 fluoride ions, which are both -1. This is aqueous, so it's going to break up into 1 barium ion, that's +2, and 2 chloride ions, but they're separate from each other. It's like CO minus, CO minus. So that 2 comes out in front. Everything here is aqueous, so you should put aqueous. Okay, some of you might notice, but hey, chlorine's by itself. Why isn't it diatomic? That's a tricky question. When they are ions, they're not diatomic. This is an ion, so it's not going to be diatomic. All right, lithium chloride, that's aqueous, so I'm going to break it up into 2 lithium ions and 2 chloride ions. Both are aqueous. All right, and this is solid, so I'm not going to break it up. It's just BAF2, and you have one of them because of the one out in front. All right, that's your full ionic equation. Should be balanced. 2 lithiums on both sides, 2 fluorines on both sides, a barium on both sides, and 2 chlorines on both sides. Now, to write our net ionic equation, I'm going to cancel out the spectator ions. Chlorine is a spectator ion. It did not change. Lithium are also spectator ions. Those did not change. But what did change was that 2 fluoride ions and a barium ion started off aqueous and separate from each other. Then they ended up getting together and forming the solid precipitate. That is the net ionic equation. It's still balanced, 2 fluorines and a barium. If we were to draw this out, the lithium fluoride aqueous would be 2 lithium ions and 2 fluoride ions floating around. The aqueous barium chloride would be a barium ion and 2 chloride ions floating around. Now, in the products, the barium and the fluoride found each other and formed that solid that's stuck together. But the lithium ions and the chloride ions are still floating around as aqueous. So that is what it would look like. Okay, I'm going to also give you the products here quickly. Now, if you actually looked at your solubility chart, you would not find the formula of these products on your solubility chart, so I'd have to give those to you. Other ones that you can find. All right, we're gonna need 2 here to balance the reaction. All right, I would pause the video and try this from start to finish without my help, guys. That's the best way to learn is if you test yourself. So please pause the video, try this out on your own before I start going through it. Okay, hopefully you just tried it out. You pause the video and let's break up everything that's aqueous into its ions. The only thing we're not gonna break up is the solid thing. So I'm gonna have 2 hydrogen ions and 2 cyanide ions. I'm going to have a copper ion. To figure out its charge, it's bound to a sulfate, which is -2. So that means that copper has to be +2. All right, all of these are aqueous because they came from aqueous compounds. All right, on the product side, I'm going to break this up because it's aqueous. It's going to break off into 2 hydrogen ions, but only 1 sulfate. And then this is a solid, so I'm not going to break it up because that's what a solid is. It's stuck together. All right, do you guys see any spectator ions? Hydrogen for sure, sulfate for sure. So we're going to have 2 cyanide ions and a copper ion. Whoop. That's aqueous. Is going to make copper cyanide. It's still balanced, and it shows the formation of the precipitate. If you guys drew what the reactants look like, this is what it should look like. Okay. Now you guys should be able to complete the net ionic equations homework as best you can. I will for sure have a office hours, sorry, forgot the word. Office hours on Schoology conferences if you would like to join from 1:30 to 2:30.